Let's turn this down. Okay. So, quick review of what we did yesterday. Alright. So, the way to learn a new programming language is to write programs. In this chapter, we'll write a program to solve a simple problem for a bookstore. Our store keeps a file of transactions, each of which records the sale of one or more copies of a single book. Each transaction contains 3 data elements. First, the ISBN, then the number of copies sold, and the third is the price. From time to time, the bookstore owner reads this file, and for each book, computes the number sold, the total revenue, and the average price. To be able to write this program, we need to cover a few basic features. In addition, we need to know how to compile and execute a program. Although we haven't yet designed our program, it's easy to see that it must define variables, do input and output, use a data structure to hold the data, test whether 2 records have the same ISBN, and contain a loop that will process every record in the transaction file. We'll start by reviewing how to solve these subproblems in C++ and then write our bookstore program. So then we started yesterday with writing a simple C++ program, and we have main returning 0. We learned how to compile it, learned how to debug it, did an exercise on what happens if you return a -1 in the place of the 0. And then we started on a new one. We have main prompting the user for 2 numbers. We take in those 2 numbers and return their sum. Learned about how cin and cout work. We have, what are they called? Input operators? Yeah, input operators and output operators, or insertion and extraction, depending on who you talk to about vocabulary. Then we have exercises. Try out the multiplication operator, done. We did all the notable exercises, but we learned comments, how and why to use comments, and why you can't do nested comments. Then we started flow of control, and we learned the while statement. And we made a program that would read off to the user the sum of 1 to 10 inclusive. And it would just do that by incrementally adding each number to a sum in the background throughout the while loop. And then went step by step how it works. Exercises we did write a program that uses a while to sum the numbers from 50 to 100. We used a decrement to subtract instead of add. And we wrote a program that prompts the user for 2 integers. And here's where we sort of went above and beyond, and we used our knowledge of Java to use an if statement and let our range print properly whether they input their numbers smaller number first or larger number first. Then we did the for statement. And the for, we have a program that does the same thing. It sums the values. This time just different formatting, basically. For loop did the same job. Exercises, we're looking at an example for loop that summed up every integer from -100 to 100 and had us guess the final value, and it was 0, and we were correct in our initial guess of 0. We rewrote some previous exercises with while loops using for loops, and then moved on to reading an unknown number of inputs. So in this example, we have while the file that the cin is reading still has values to read, we will take each value and add it to our sum, and as soon as while no longer has any values, it will move on, and then we will print the sum. And this is just another way to do it with the same sum of all numbers in a range problem. Oh, and we also learned how to manually enter an end of file, which was Control-Z. And then we formally learned the if statement with a more complex, sort of nested flow of control statements. We have the current value and the value, and we want to read the first number from current value, increase our count by 1, and while there is still values to read, if that value is equal to if the next value is equal to the current value, so the first one, increase the count, and otherwise output how many times that current value occurred in a sequence before changing, and then change the current value to the new value so that we can go through the loop again for each number in the sequence. Down here we have the example where they give us 42, 42, 42, 42, 42, 55, 55, 62, 100, 100, 100, and it tells us that the output should be 42 occurs 5 times, 55 occurs 2 times, 62 occurs once, and 100 occurs 3 times. And we did get that. What the exercises then were showing us is that this program does not account for counting up numbers separated from one another. So if there was a 42 at the beginning and then another 42 at the end separated by some other digits, it would say 42 occurs once, and then it would say how many there are of all these other digits, and then it would say 42 occurs once at the very end again. It's not smart enough to keep track of the whole file before printing anything out, which was fine. And then 1.5, we just started on introducing classes with 1.51, the sales item class, which I had downloaded and is now available for use from the textbook website. And we'll learn more about it apparently in later chapters, but for now we're just going to use this sales item class. And we learned how to read and write sales items, adding sales items, and did the exercise of downloading it, writing a program that reads two items and produces their sum, as well as reads several transactions for the same ISBN and writes the sum of those. Those exercises we did yesterday and then we finished. So, 1.5.2 now. First, look at member functions. Our program that adds two sales items should check whether the objects have the same ISBN. And here's how we'll do it. And here's some code. So let me copy this code. But before doing that, I want to grab sales item. And we're going to throw it in with our 1.5.2 repository so that when I include it, it knows what to do. Oh, we also needed version test. Yeah, that's right. Forgot about that. Sweet, it works. Even though it's still telling me I have an error here. Whoops. Didn't know I could right click that and have it open. Anyway, yeah, this is what I was saying earlier. It's the code in this file is explained in chapter 7 and 14. Don't try to understand it until you've read those chapters. So we'll ignore that for now. We want our code to, I'm gonna bring this one closer. We want it to say, we're going to define a sales item, item 1 and item 2. And we're going to take in those items. And according to this comment, first check that item 1 and item 2 represent the same book. Right, so this first section is our program adds two items to check whether the objects have the same ISBN. So we're doing that here with an if item 1 dot ISBN is equal to item2.isbn. Then we want to output to the user item1 plus item2 . Oh, we just want to be able to indicate success with a return statement. So we're just going to do an end line followed by return 0. Else output to the user, hey, hey, data must refer to the same ISBN, and then we'll return a -1 to indicate failure. And now this code is the same as the one in the textbook. So let's go through what the textbook has to say about it. The difference between this program and the previous version is the if and its associated else branch. Even without understanding the if condition, we know what this program does. If the condition succeeds, then we write the same output as before and return 0, indicate success. And if it fails, then we execute the block following the else, and that will print a message and return an error indicator. So this section is about member functions, and that's where we see the ISBN parentheses, and it's the ones right up here. The if condition calls a member function named ISBN. A member function is a function that is defined as part of a class. Member functions are sometimes referred to as methods. I've heard both in Java. Ordinarily, we call a member function on behalf of an object. Oh. Gotta drink water. We have an object. For example, the first part of the left-hand operand of the equality expression, item1.isbn, uses the dot operator, the period symbol, to indicate that we want the ISBN member of the object named item1. So the dot operator indicates the following is a member of the previous, or a method. It applies only to objects of the class type, and the left-hand operand must be an object of class type, and the right-hand must be a member of that type. The result of the dot operator, oh, just a member, it doesn't have to be a function. So, like, yeah, that makes sense. It could be a variable. It doesn't have to be a function. When we use the dot operator to access a member function, and I forgot to start my timers, so let me quickly throw on a 30-minute timer for myself to take a break, because we've been streaming for 20 minutes. Okay. When we use the dot operator to access a member function, we usually do so to call that function. We call a function using the call operator, which is the parentheses. And it encloses a possibly empty, in this case, list of arguments. The ISBN member function does not take an argument, thus it is empty. By calling this function, it returns the ISBN stored in item 1. The right-hand operand of the equality operator executes in the same way, returning the ISBN stored in item 2. So this if statement can be thought of as replacing the section here with the ISBN input by the user here and here for the second one. And if the ISBN on the left, which should be a sequence of symbols, is equal to the sequence of symbols for the item 2's ISBN, then we'll do this code. And if it's not the same, then we'll do this code. Sweet. We're now ready to solve our original bookstore problem. We need to read a file of sales transactions and produce a report that shows for each book the total number of copies sold, the total revenue, and the average sales price. We'll assume that all the transactions for each ISBN are grouped together in the input. Our program will combine the data for each ISBN in a variable named total. We'll use a second variable named trans to hold each transaction we read. And if trans and total refer to the same ISBN, we will update total with that transaction. Otherwise, we'll print total and reset it using the transaction we just read. So this is 1.6, and I never did the exercises, so let me do that real quick. Exercise 1.23 for the previous section, referring to reading two ISBNs that are the same. We want to write a program that reads several transactions and counts how many transactions occur for each ISBN. So how do we... This is actually a great time to go back to the previous code. I want to open up the previous project because it does this current value thing. Oh, this one doesn't. Which one is it? There it is. So we define our two variables, and then if that input has values to read, then we'll increase the count. What's the exercise say? What do we want to count? How many transactions for each ISBN? Yeah, this is the same problem. So we'll take in an item, and then we will increase the count. And while there is more items to read that we will take into our other variable, If they are the same ISBN, which we will use the method operator, we will further increase the count, else we will do the rest. So let me do that over here. Let's do this first. And then we will do 2 sales items. And we will say sales item current item. We'll do it the same way as we did before, and item, sure, whatever. It's not particularly evocative of what it's supposed to mean, so it's not a great variable name, but we're going to copy this formatting. And then we want to say while there is something to take in, we're going to take it into current item. And we will say create a counting variable, starts at 0. Starts at 1, because we want to increment it right at the start. Well, at this point in the code anyway. And then we're going to do the same thing, but this time take it into item. And now here's where we check the ISBNs. If current item dot ISBN call function is equal to item.isbn so if they are the same, then we want to increase our count. Otherwise, we are no longer counting anymore. And we want to output how many there were for that ISBN, change the current value to the new one, and reset the counter. Because we're never coming back up to here until there are no more items to read. We're just going to keep going to here. So output to the user, and we'll say how many transactions for each ISBN. So we'll actually say that ISBN has count transactions. And then end it. Take our new variable. And reset the count. Now, because when we do this, we'll count the first one into this, but when we get to the last one in this else, we're going to come up here and there will be no more variables to read when it gets to the last one. So it's not going to come back in here and print. We have to print it here while count still exists. So right here, we will output to the user that same thing. And that'll do it. So let's throw some comments on here. Create sales item containers. While there are peak. While there are items in the file to read, we will create a counting variable. While there are items in the file to read, this is doing the same thing, but we're taking it to the other item. So take the first item into current item. Create a counting variable for that first item. And then while there are items in the file to read, again, take the next item into item. If current item and item have the same ISBN, increase the count. Else, we have reached the end of that number of ISBN transactions, so we need to output that and say, or output to user am I muted? No. Okay. So else we have reached a new ISBN. Oops. So we want to output the previous or first ISBN's number of transactions, and then we will reset and output the final ISBN's number of transactions. And there we go, that's our comments. Sweet. Next exercise. Test the previous program by giving multiple transactions representing multiple ISBNs. The records should be grouped together. Okay. Test exercise 1.24, and that's it. So let's just do that then. Debug first. No problems. Let's get some prompts in here. Input 2 items. And we'll say this is 5.2, and then end that line. And down here we will say input any number of sales items grouping ISBNs together. Okay, now we'll run our program and we'll know sort of what we're supposed to be doing. And let's go, there was example ISBN codes, yeah, right here. I don't think they need to be that long, so we'll say ISBN 1 is 321321. It has 3 transactions at $20, and ISBN number. We'll test our failure right here, or else. Data must refer to the same ISBN, and we'll say 333333, and there's 5 of them, and it's $19. Data must refer to the same ISBN, and the code works out, right? Because it's actually going to return. So I actually need to comment these out, so the code doesn't just end there. We'll do the same thing, except this time we will say this, and that's the same. And there's 5, 4, 7. Sweet. So when we switched ISBNs, it was like, okay, we've reached our else condition, so we're going to say how many transactions there were before moving to the next item. This is it moving to the next item right here. Later on, I'm sure we'll have file input output, so we can create an entire pre-created list of ISBNs. But this worked exactly the way we wanted it to. We could have kept going. That does say though, like, or that does tell me rather, that if you were to do that and it reads this list from a file, like a text file, then it's going to say only these lines, right? You're not going to see the ISBNs. Or rather, you're not going to see the sales information. You're only going to see the number of transactions each one had, which is fine. Okay, we have done the exercise. Let's do our bookstore program now. And that means a new project. And that will also be the end of the chapter, once we're done. Now this also uses sales items, so let me do that first. Grabbing both of those. Putting them in here so that we can include them. And then I'm going to take this because I don't want to lean over so far. And you can see our timer, we're almost out of time anyway. Before I take a break, let's see if we can get all this in here. We should be able to, I think. So sales item total variable to hold data for the next transaction, and then we want to read the first transaction and ensure that there are data to process, and then we will do that, and that will look like if the input has items in it, then they will go into the total. And the sales item trans for the transaction. Say while there is data to process, we will take it into transaction, and if we are still processing the same book, so if totals ISBN call is equal to trans ISBN call, then total plus equal trans. We will update the running total, else print results for the previous book. And set the total to the transaction that we're currently running. Total now refers to the next book. Print the last transaction. This is like literally the same exact thing we just did. Well, it's not quite the same, but it's very close. Now, else down here is going to apply to this if statement. So if there is no input to be had when we first run this, we want to, according to the textbook, and I agree, no input, warn the user. And we're using C error for the first time. Console, right? So what C stands for, I'm not sure. C error, C in, C out. What was the last one? C log. No data. And return a failure state. And that's it. That is, we did it. We have a minute remaining. This program is the most complicated one we've seen so far. But it uses only facilities we've already seen. As usual, we begin by including the headers, and inside main we define an object named total, which we'll use to sum the data for a given ISBN. We'll start by reading the first transaction into that total and testing whether the read was successful. If it fails and there are no records, we fall through to the outermost else branch, which tells the user there's no input. Right. Assuming we successfully read a record, we execute the block following the outermost if. It starts by defining an object named trans, which will hold our transactions as we read them. The while statement, let me just finish this then. The while statement will read all the remaining records. As in our earlier programs, the while condition reads a value from the standard input. In this case, we read a sales item object into transactions. As long as the read succeeds, we execute the body of the while. Inside of this body, there is a single if statement, and it checks whether their ISBNs are equal. If they are, we use the compound assignment operator to add transaction to total by assigning trans to it. Oh no. To add trans to the total. If the ISBNs are not equal, we print the value stored in total and reset total by assigning trans to it. I skipped a line while reading. After executing the if, we return to the condition in the while statement while reading the next transaction, and so on until we run out of records. When the while terminates, Total contains the data for the last ISBN in the file, and we write the data for the last ISBN in the last statement of that block, and conclude the outermost if statement. Using this header from the website, compile and execute the bookstore program in this section. Okay. It shouldn't, I mean, we're not giving it any input though, is the problem. So if I do this, it says no data. Does the textbook come with sample data files are in the data directory? Yeah, it does have an example. Can I copy paste this into the console? Does that work? It does. Doesn't quite work though. Why is this different? Oh, it's because it's doing it. It's not saying it's doing it though. So it reads the first file. Right, it's reading this whole thing, but it's saying, here's the first ISBN, here's the second one. They're not the same, so let's print out the first one. And, oh look, here's a new one, and it's not the same as the second one, so we're going to print out the second one. And here's this third one, and the third one is the same, is the same, is the same. And here's one that's not. So every time it goes to a new one, the following line is our output from our program, telling us what the total is. So I don't want it to read out like that. That is very, not very much information. We'll say, total.isbn. Oops. Has the following information. And this is not going to be super pretty because it's going to say the ISBN twice now, but at least we'll be able to properly delineate when this is happening. Yeah. I could have even just put a bunch of spaces in there. But yeah, it's working now. Sweet. Well, let's do a quick save, and I'm gonna go take a break. So back in. Take a break. Start. Okay, I'm back. Okay. So we've run through this. Exercise using this header from the site, compile and execute the program. We did that. Yeah, these are just text files. I don't know why they're saying they're files. It's weird. Okay, well, we did the exercise, so next page. Chapter summary. This chapter introduced enough of C++ to let you compile and execute simple C++ programs. We saw how to define a main function. We saw how to define variables, do input-output, write if, for, and while statements, and closed by creating a class. In this chapter, or rather we didn't create a class, we introduced the class by using a class and its methods. So, we got a bunch of terms. Let's see if there's any I don't recognize. Argument, assignment, block, buffer. A buffer, that's what end line closes out, right? It's a region of storage used to hold data. Input-output facilities often store input or output in a buffer and read or write the buffer independently from actions in the program. They can be explicitly flushed. By default, reading input flushes output, and output is also flushed when the program ends. Built-in type, cerr, cin, cout, clog, character string, literal. It's just a string. Class, types, comments, conditions. Namespace. Namespace was like STD standard. If we set up here using namespace STD, and there's like a way to do it that that we wouldn't have to say it every time. All those could be just said once in the top using namespace. Yeah, so STD is a namespace. And it's the name of the standard library. It's the namespace of the standard library. A whole bunch of different operators, including And that's it. Now we're on to part 1. The basics. The previous section is just called Getting Started. Okay. Every widely used programming language provides a common set of features which differ in detail from one language to another. Understanding the details of how a language provides these features is the first step towards understanding it. Among the most fundamental is built-in types, such as integers, characters, and so forth, variables, which let us give names to those objects, to various objects, expressions and statements to manipulate values, control structures like if and while loops that allow us to conditionally or repeatedly execute sets of actions, and functions that let us define callable units of computation. Most programming languages supplement these basic features. They let programmers extend the language by defining their own types and provide library routines that define useful functions and types not otherwise built into the language. Okay, so this is the header for part 1, which I'm going to continue reading in a second, but I got confused because I saw part 1 and then chapter 2, thinking this said chapter 1 for some reason. So part 1 begins with chapter 2, and this is the header for it, followed by the header for chapter 2 with its contents. Okay. So in C++, as in most programming languages, the type of an object determines what operations can be performed on it. And whether a particular expression is legal depends on the type of the objects in that expression. Some languages, such as Smalltalk and Python, check types at runtime. In contrast, C++ is a statically typed language. Type checking is done at compile time. As a consequence, the compiler must know the type of every name used in the program. C++ provides a set of built-in types, operators to manipulate those types, and a small set of statements for program flow control. These elements form an alphabet from which we can write large, complicated real-world systems. At this basic level, C++ is a simple language. Its expressive power arises from its support for mechanisms that allow the programmer to define new data structures. Using these facilities, programmers can shape the language to their own purposes without the language designers having to anticipate the programmer's needs. Perhaps the most important feature is the class. In C++, such types are sometimes called class types to distinguish them from the types that are built into the language. Some languages let programmers define types that specify only what data make up the type. Others, like C++, allow programmers to define types that include operations, as well as data. A major design goal of C++ is to let programmers define their own types that are as easy to use as the built-in ones. The standard library uses these features to implement a rich library of class types and associated functions. The first step in mastering C++ is learning the basics of the language and library is the topic of Part 1. Chapter 2, which we're about to go into, covers the built-in types and looks briefly at the mechanisms for defining our own new types. Chapter 3, so this is, I guess, just going to talk about the table of contents. Chapter 3 introduces two of the most fundamental library types, strings and vectors. That chapter also covers arrays, which are a lower level data structure built into C++ and many other languages. Chapters 4 through 6 cover expressions, statements, and functions. This part concludes in Chapter 7, which describes the basics of building our own class types. As we'll see, defining our own types brings together all that we've learned before, because writing a class entails using the facilities covered in all of Part 1. Okay, Chapter 2. Types are fundamental to any program. They tell us what our data mean and what operations we can perform on those data. C++ has extensive support for types. The language defines several primitive types, like characters, integers, floating point numbers, etc., and provides mechanisms that let us define our own data types. The library uses these mechanisms to define more complicated types, such as variable length character strings, vectors, and so on. This chapter covers the built-in types and begins our coverage of how C++ supports more complicated types. So the first part that I'm going to put code for looks like it doesn't really happen. For a while. Look at this. Oh no, we got some exercises. Okay. Yeah, because it's like section 2.1.1 has exercises that are just questions, but once we get to 2.1.2, we have a exercise that says write a program to check whether your predictions were correct based on the previous question. So we're not going to be coding for a little while here. So I'm just going to scoot over here so I can read it. Okay. Types determine the meaning of the data and operations in our programs. The meaning of even as simple a statement as I equals I plus j depends on the types of I and j. If I and j are integers, this statement has the ordinary arithmetic meaning of addition. However, if I and j are sales item objects, this statement adds the components of these two objects, like we saw in section 1.5.1. Which I'm not going to bother opening over here, but we have done recently. 2.1, primitive built-in types. So C++ defines a set of primitive types that include the arithmetic types and a special type named void. Can I also say how nice it is to write a program that just starts with int main and not public static, what's it called? Public static void main string args to start every program. Like, this is how you do that in Java. Int main is how you do it in C++. Crazy. The arithmetic types represent characters, integers, and Boolean values and floating point numbers. The void type has no associated values and can only be used in a few circumstances, most commonly as the return type for functions that do not return a value. So if we created a function in a class that did things but returned nothing to whatever called it, it would have the type of void. Arithmetic types. Or arithmetic types, however you prefer to read that. The arithmetic types are divided into two categories: integral types, which include character and Boolean, and floating point types. The size of, which is to say the number of bits in the arithmetic types varies across machines. The standard guarantees minimum sizes as listed in table 2.1 right here. However, compilers are allowed to use larger sizes for these types. Because the number of bits varies, the largest or smallest value that a type can represent also varies. Okay. I don't think I really need to get into what this is. It's just saying different types have different minimum sizes. Which will be an optimization thing, I'm sure, at some point, but not right now. The bool type represents the truth values of true and false. We know that. The remaining character types of character is big enough to hold numeric values corresponding to the characters in the machine's basic character set. In other words, it's a single byte. The remaining character types of wchar_t, char16_t, and char32_t are used for extended character sets. Let's just going through this table now. wchar_t type is guaranteed to be large enough to hold any character in the machine's largest extended character set, and the following types are intended for Unicode characters. It's a standard for representing characters used in essentially any natural language. The remaining integral types represent integer values of potentially different sizes. The language guarantees that an int will be at least as large as a short, long is at least as large as an int, and long is at least as large as long. Type long was introduced by the new standard. Mind you, this is not a super recent printing of this textbook. Yeah, it even says right here C++11, which I believe we're pretty far beyond that. It might even refer to the year. That might be 2011. Yeah, it's publication year. And this textbook is for C++11, but we've now gotten up to C++20. Despite that, however, as of June 7th, 2022, this book, C++ Primer 5th edition, published for C++ 11, is still considered the best C++ programming textbook, even as late as the C++ 20 version, standard, whatever. So the new stuff must be pretty niche by comparison to this reference manual. Okay, moving on. Machine level representation of the built-in types. So computers store data as a sequence of bits in binary. Most computers deal with memory as chunks of bits of sizes that are powers of 2. The smallest chunk of addressable memory is referred to as a byte. The basic unit of storage, usually a small number of bytes, is referred to as a word. In C++, a byte has at least as many bits as are needed to hold a character in the basic character set. On most machines, that's 8 bits, and a word is either 32 or 64 bits, that is 4 or 8 bytes. Most computers associate a number, called an address, with each byte in memory. On a machine with 8-bit bytes and 32-bit words, we might have a word of memory that looks like this table, where this is a word and each one of these lines is a byte, and that byte has a memory address number. Yeah, so here's the byte address on the left with 8 bits of the byte following the address. And we can use the address to refer to any of several variously sized collections of bits starting at that address. It is possible to speak of the word at address ending in 424 or the one ending in 427. To give meaning to memory at a given address, we must know the type of the value being stored there. The type determines how many bits are used and how to interpret those bits. If the object at location ending in 424 has type float, and if floats on this machine are stored in 32 bits, then we know that the object at that address spans the entire word. The value of that float depends on the details of how the machine stores floating point numbers. Alternatively, if the object at its location ending in 424 is an unsigned character on a machine using an ISO-Latin one-character set, then the byte at that address represents a semicolon. So this is a semicolon under these conditions. Gee whiz. Okay. My voice is getting tired, which is why I'm making this visible. Looking forward to stopping talking. Okay, the floating point types represent single, double, and extended precision values. The standard specifies a minimum number of significant digits. Most compilers provide more precision than the specified minimum. Typically, floats are represented in one word, doubles in 2 words, and long doubles in either 3 or 4 words. The float and double types typically yield about 7 and 16 significant digits, respectively. So we can get 16 significant digits with 64 bits of memory, which is 8 bytes. The type long double is often used as a way to accommodate special purpose floating point hardware. Its precision is more likely to vary from one implementation to another. Okay. Unsigned and signed types. Except for booleans and the extended character types, the integral types may be signed or unsigned. A signed type represents negative or positive numbers, including 0. An unsigned type represents only values greater than or equal to 0. The types int, short, long, and long, long are all signed. We obtain the corresponding unsigned type by adding unsigned to the type, such as unsigned long. The type unsigned int may be abbreviated as unsigned. Okay. That's just like not really relevant to me right now. Unlike the other integer types, there are 3 distinct basic character types: character, signed character, and unsigned character. In particular, character is not the same as signed character. Although there are 3 character types, there are only 2 representations, signed and unsigned. The plain character type uses one of these representations. Which of the other 2 character representations is equivalent to each character depends on the compiler. In an unsigned type, all the bits represent the value. For example, an 8-bit unsigned character can hold the values from 0 through 255, including it. The standard does not define how signed types are represented, but does specify that the range should be evenly divided between positive and negative values. Hence, an 8-bit signed character is guaranteed to hold values from negative 127 through 127. Most modern machines use representations that allow values from negative 128 through 127. So of the 255, they put one of the leftover one that cannot be split evenly on the negative side. Okay, advice: deciding which type to use. C++, like C, is designed to let programs get close to the hardware when necessary. The arithmetic types are defined to cater to the peculiarities of various kinds of hardware. Accordingly, the number of arithmetic types in C++ can be bewildering. Most programmers can and should ignore these complexities by restricting the types they use. A few rules of thumb can be useful in deciding which type to use. use an unsigned type when you know that the values cannot be negative. So these are optimization things, I believe. Use int for integer arithmetic. Short is usually too small, and in practice, long often has the same size as int. If your data values are larger than the minimum guaranteed size of an int, then use long. Do not use plain character or boolean in arithmetic expressions. Use them only to hold characters or truth values. Computations using character are especially problematic because character is signed on some machines and unsigned on others. If you need a tiny integer, explicitly specify either signed character or unsigned character. Use double for floating point computations. Float usually does not have enough precision, and the cost of double precision calculations versus single precision is negligible. In fact, on some machines, double precision operations are faster than single precision. The precision offered by long double usually is unnecessary and often entails considerable runtime cost. So if we want to use decimals, use the type double. Okay. Exercise 2.1. What are the differences between int, long, long, and short? And that would be the amount of memory that they take and the precision and guaranteed number of digits. Yeah, minimum size and anyway, okay. Between a float and a double. Size and precision. Double is double precision, and it's also 10 significant digits to floats 6. To calculate a mortgage payment, what types would you use for the rate, principal, and payment? Principal, payment. I mean, double for the rate, because float, as they suggested, is not really useful most of the time. I feel like I could get away with float for a rate that small, but double. And then principal is the total size of the loan, right? So that's typically 6 digits. But if you want to include pennies, you need 8, which is going to be a double. And payment, again, you need decimals, so either float or double, and I would use a double because it suggests using double over float most of the time. Really not a great question, I don't think. Okay. 2.1.2 type conversions. The type of an object defines the data that an object might contain and what operations that object can perform. And I'm seeing these now, symbols on the margins. And there's one over here. And I want to know what they mean with these symbols, because they've started showing up more now. They weren't really in the first section. So let me bookmark and find out what these symbols mean. So here's explaining it. We've marked sections that cover the fundamentals of the language with the person studying a book image, the same one we saw here. Fundamentals. So this means fundamentals, and you should study it. We've also indicated those sections that cover advanced or special purpose topics that can be skipped or skimmed. They've been indicated with a stack of books to indicate that you can safely put down the book at that point. It's probably a good idea to skim them so you know that they exist, but there's no reason to spend time on them. And to help readers guide their attention further, we've noted particularly tricky concepts with a magnifying glass. So these symbols are all about how much focus you should give a section. Less focus, more focus, and then standard. No, it's actually this reading guy is more focus, this is less focus, and this is a lot of focus. In the hopes that the reader will take the time to understand thoroughly the material presented in magnifying glass sections. Yeah. Okay. So this is saying pay attention. And here on the very next page, the camera can't see it, is our first magnifying glass. Okay, let's dive into it then, right? We've still got 11 minutes. The type of an object defines the data that an object might contain and what operations that object can perform. Among the operations that many types support is their ability to convert objects of the given type to other related types. Type conversions happen automatically when we use an object of one type where an object of another type is expected. We'll have more to say about conversions in section 4.11, 120 pages from now. But for now, it is useful to understand what happens when we assign a value of one type to an object of another type. And here's some examples. Boolean b is set equal to 42. A boolean is typically either true or false. In this case, 42 is read as true. If we set int I, an integer, equal to the value of b, it will not be 42. I will have the value of 1, so true is 1. And positive integers are also true, or they are converted to true. If we say that I is equal to 3.14, an integer can't have decimals, or an int can't have decimals, it will simplify to 3. And then if we convert that int, which has a value of 3, to a double, and we say double pi is equal to I, pi will then have a value of 3.0. So by converting an int to a double, we just add 0.0 to the end. Unsigned character C equals -1. And now, because it's unsigned, it shouldn't have a negative number. So when we put a negative in there, it automatically converts it to, it says, assuming 8-bit characters, C has value 255, so it loops back around to the end. And if we say signed character C2 is equal to 256, which should only go from about -128 to 127, and we're going above that, then assuming 8-bit characters, the value of C2 is undefined. So if we try to do something with C2, it's going to say that thing is undefined. So what happens depends on the range of the values that the types permit. When we assign one of the non-bool arithmetic types to a bool, the result is false if the value is 0 and otherwise true. So actually any non-zero becomes 1 or true. When we assign a boolean to one of the others, the resulting value is 1 if it's true and 0 if it's false. When we assign a floating point value to an object of integral type, the value is truncated. The value that is stored is the part before the decimal point, so it's not rounding. If it was 3.9, it would still say I has a value of 3. It just gets rid of everything. It ignores everything from the decimal onward, including the decimal. When we assign when we assign an integral value to an object of floating point type, the fractional part is 0. Precision may be lost if the integer type has more bits than the floating point object can accommodate. If we assign an out-of-range value to an object of unsigned type, which is what happened with character C, the result is the remainder of the value modulo the number of values the target type can hold. For example, it can hold values from 0 through 255. If we assign something outside of this range, the compiler assigns the remainder of that value divided by, or modulo 256. Therefore, assigning -1 gives the object a value of 255. If we assign an out-of-range value to a signed type, the result is undefined. The program might appear to work, it might crash, or it might produce garbage values. Advice: avoid undefined and implementation-defined behavior. Undefined behavior results from errors that the compiler is not required and sometimes not able to detect. Even if the code compiles, a program that executes an undefined expression is in error. Unfortunately, programs that contain undefined behavior can appear to execute correctly in some circumstances and/or on some compilers. There is no guarantee that the same program compiled under a different compiler, or even a subsequent release of the same program, or of the same compiler, will continue to run correctly. Nor is there any guarantee that what works with one set of inputs will work with another. Similarly, programs usually should avoid implementation-defined behavior, such as assuming that the size of an int is a fixed and known value. Such programs are said to be non-portable. When the program is moved to another machine, code that relied on implementation-defined behavior may fail. Tracking down these sorts of problems in previously working programs is mildly put unpleasant. The compiler applies these same type conversions when we use a value of one arithmetic type where a value of another arithmetic type is expected. For example, when we use a non-Boolean value as a condition, the arithmetic value is converted to Boolean in the same way that would be converted if we had assigned the arithmetic tool to a bool variable. In other words, this next section of code right over here is int I equals 42. If I being treated as a Boolean returns true, then set I equal to 0. And that's basically what it says. If the value is 0, the condition is false, and all other values yield true. By the same token, when we use a Boolean in an arithmetic expression, its value always converts to either 0 or 1. As a result, using a Boolean in an arithmetic expression is almost surely incorrect. Yeah, you wouldn't want to say, in math, you can say like 2 plus 2 equals 4. You wouldn't say true plus true equals 2. You're going to be correct in the compiler sense, where Boolean's true statements are equal to 1, but that's not how you should do things, is what it's saying. And with 45 seconds left, and this next section being a study closely section, I'm going to call it here. I need like a paperweight. Okay. Day 2 complete. We went from page 22 to page 36 in 2 hours-ish. So 7 pages per hour. It's pretty slow, to say the least. It's like 10 minutes per page. But we're spending a lot of time on the code, going over things, double checking things, looking things up, grabbing compiler stuff, whatever else, header files, yeah. I mean, at 10 minutes per page, the index to supplemental sections. So the textbook actually ends on page 864. 10 minutes per page, that's 8,640 minutes. $8,640 divided by 60 minutes, 144 hours by 40 hours per week. We get done with the textbook in 3.5 weeks. If we do 40 hours per week. I don't need to do the entire textbook. I need to do up to the point where I can be studying algorithms. So I want to know what I learned in Java basically in C++, which is like binary search trees and maps. Let's see. Part 2, the C++ library, input output, iterators, sequential container operations, string operations. Generic algorithms is chapter 10. Associative containers, dynamic memory. So associative containers includes map information, dynamic arrays, pointers. So we definitely want part 1 and part 2. Overloaded operations and conversions. I mean, I'll be pretty happy if I get through part 2. And I think I'll have leftover time if I keep my study game up strong. And with that leftover time, I want to make sure I want to make sure I self-study some other topics. I don't know if they're in this textbook or not, though, looking at it. Stuff like, what's it called? When you have a method... recursive. Recursive is the word. Recursive in C++. Is C++ recursion? It doesn't look like it's in this textbook. Yeah, so I'm gonna get through parts 1 and 2, which is closer to 500 pages. So 5,000 minutes in 2 1/10 weeks at 40 hours a week, which I'm currently doing way less than, because we did 3 hours yesterday, 2 hours today. That's 5 for the week. And we need 83 hours. 83 hours across. Have 4 weeks, effectively. I need to be doing 21 hours a week minimum to get through parts 1 and 2. If I do 30 hours a week, I hit 83.3 in less than 3 weeks, giving me an extra week of study time for something else, and that's what we want. So I need at least 30 hours a week, preferably 40. 30 to 40 a week. We'll do it. Okay, that's it for today.